So also we'll talk about how to make it large scale, building this personalized decision model scalable, and most importantly, we will actually learning this models through preference feedback. So that's the third component. Okay, why it's not working now? Okay, that's the third component. Let's get into the broad picture of the motivation of my work in general. So the broad goal is actually to, some of the titles are getting a bit off, but I think it's fine. So the broad goal of my work is actually to use machine learning models for assisting human better. It could be for assisting elderly, for child, I mean like automated learning, for automated learning or automated online learning, for kids or any sort of courses, personalized assistance, personalized healthcare, different kind of complex decision tasks, where the goal is to actually design human-aligned, scalable, effective machine learning algorithms for real-world prediction tasks. So let me come to the first part. So what is a prediction model? So that's probably already obvious to most of us, but let's see. So by and large, I call a prediction model is basically a mapping from a context to a decision space. So if I consider a very simple early classical prediction model, it could be a binary classification. It could be a spam filtering kind of prediction model where the context space is basically the email and the user who is receiving the email. So that could be the context. And the prediction space could be just a 0-1 binary feedback, whether the label of the email is spam or not spam. And it could be zero, it could be just encoded by 0-1 feedback. So the prediction model is just a mapping from this context, general context space C to this decision space D. Earlier prediction models were easy to design. So for example, in this case, we know that how do we actually train such a prediction model? So we might have a class of hypothesis, which could be this capital H, or that could be the class of all linear predictors or polynomial predictors or RKHs, whatever your favorite decision class could be. And then we design some loss functions. So if the loss is actually correctly classifying a spam email as a spam, then we assign it to 0. A loss, if it is actually like correctly predicting a clean email as a clean, then we also assign a 0 loss. If it mispredicts, we assign a 1 loss. And then we have some already training label data. We just need to minimize, do some regularized empirical loss minimization over the training data over our hypothesis class H to figure out what is the best fitting hypothesis in the hypothesis class. And that should basically give us the best kind of predictor. Okay, so that's very easy task, and so by far we know it. It's almost like the first or second lessons we get in our machine learning modules. But this loss function, designing this loss function is very critical to the task we have in hand. The issue is in modern prediction systems, as we try to throw this machine learning prediction algorithms to more and more complex and long-term decision tasks, starting from healthcare to stock market prediction to autonomous driving. Autonomous driving, robotics, recommender systems, fraud detection, and all the recent craziness about this large language models. All of this actually are some prediction models. But these are much more long-term and complex prediction tasks. It's not even also obvious at the first place that what the loss function should be. How do we actually train this complex decision models? Let's see how we actually could run into like grave problems for some very simple tasks. For example, you have a robot. So this is in the context of robotics, and your room is really unclean. So you just want your robot to clean up the room. Maybe this is your office space, and you want your robot to clean up the room, and then you someone actually designed a loss function for this task. So the loss function could be, if you see a dirt, if the visual sensor of the robot actually senses dirt, it sees dirt, then you give it a loss of -10, or give it a loss of +10, give it a reward of -10. Or if it collects dirt, then it gets a reward of +5. So obviously the loss function is designed so that the robot should not, it would try to maximize the reward. It should try to collect the dirt and not see the dirt. Okay, then you go for the class lecture or whatever, and you come back after an hour and you see the robot has only done this after an hour. So what it has done is it did not clean up the room at all. It just covered the visual sensors by a bucket through which it was supposed to clean the room. Why? Because the loss is just misaligned with what you actually want the robot to do. So oftentimes the problem with machine learning prediction models is you are designing, you want to do something else, but your loss is probably misaligned so that it's just trying to minimize the loss, but it's doing completely different thing. It's just trying to minimize the loss as much as possible. It's not really able to understand what you intend to do. So human expressions are somewhere lost in the process. So this is a classical example of reward hacking. There could be also similar problems of reward safety in reinforcement learning or prediction tasks. For example, if you ask your robot to fetch the coffee, and maybe you have just like optimized the time and the distance covered in the entire process, and the robot essentially could hurt a baby or break a vase in the process of minimizing the time and the distance, because that's all it has learned. It doesn't care about what is going on in the outer environment. So this is the problem of reward safety. Similarly, designing recommender systems, it's very unclear that what are we trying to optimize? What is the notion of loss or reward in the long term that we're trying to optimize? So these are some classical problems that we run into when we have learning from preference, when we have this classical real world prediction problems. So let's take a step back and think, are we training the machine learning models wrong? So in general, how are we making the decisions? Because essentially what we are trying is to teach our machines to take the right decisions in a human aligned way. So whatever our intention is, we want the machines to teach that through some feedback, through some coding. But through the loss function or through the classical ways, it's going kind of wrong. Kind of like machine is not trying to understand, not able to understand what you're intending to do through the machine. So how do we make decisions? Let's try to understand it. Generally, we don't care much about real numbers, or we don't think much in terms of real numbers. What do I mean by that? Is suppose this morning I had to commute from my hotel to the department, and suppose if I'm driving, the Google map might show me 3 different options, option A, B, C. And my goal would be just to choose the route which has the lowest commute time, which is probably like the most pleasant to drive, the most least congestion. And I will just pick one route A, which satisfies all of this. I'm not going to assign rewards to these routes before choosing the route I prefer. So I'll kind of relatively make a decision that, yeah, overall, I think I like this route A or route C over A and B because so and so reasons. I'm not really encoding a number before picking which is my favorite decision. Similarly, if I ask you this question, if I ask you 2 kind of questions, I show you 5 movies, and I just ask you either you rate the 5 movies in a scale of 0 to 10, or I alternatively say you could just pick your favorite movie, or just pick your first 2 favorite movies. Most of the time, the experiments has been conducted, and it has been proved that generally the second option is much more preferable for humans to elicit, because this is like much more easier task for us, and we can express ourselves much better in a relative scale. That's the same trick the doctors also use when they try to understand which is the best fitting lens for our eyeglass. If we need to encode it in a more mathematical framework, so essentially consider, so the idea is we all have some preferences in our head. So we have some options available for a given task, for a given situation, or at a context. We have some options available, and we generally have some preference matrix. And we generally make this decision from this preference matrix. So what does it mean is, suppose I have this 5 movies, and generally what I mean by a preference matrix is a 5 cross 5 square matrix, where every entry of the square matrix defines a probability. Suppose I choose a row, which is the second row, and the fourth column. So 0.5 is denote basically the probability through which probability by which I like movie 2 over movie 4. Okay, so each of us might have our individual preferences, but this is something we have in our head. Whenever you show me two movies, generally probably whenever you show me movie 2 and 4, I'm going to that entry and I'm trying to toss a binary coin, binary random variable. If it is 1, I say I like 2 over 4. If it is 0, I say the other way around. That's how maybe I'm making the decision, because humans are not most always not exactly correct. So there could be noises in the decision, but it could be a very reliable way to taking decisions in this way. Of course, as an algorithm designer, I don't know what this preference matrix is. Kind of the goal of the system is to teach that this is my preference matrix and this is how you should take the decision. This could be a goal, because the preferences actually, humans are much more expressible, and preferences can encode the safety and the human intention much better than what we can teach them through these rewards. In fact, many studies of neuroscience and brain and human perception have shown that humans are much more comfortable and expressive in making decisions on a relative scale.
So this preference matrix, does there have to be some transitivity rule that it satisfies? Because suppose I prefer 1 over 3 and 3 over 4.
Yeah.
So there needs to be some consistency, right? That I would probably then prefer 1 over 4.
Maybe not always that can happen.
So
it can be arbitrary. Yeah. So that's one of the challenge. Of course, if you don't have any transitivity, it's harder to define what is a good decision space. Because if you have transitivity, it's slightly easier to deal with such preferences. You can try to find this total ordering ranking, but if you don't have it, then what is it that you are trying to optimize? So we'll see that, but it's a good question. I mean, we generally don't assume any such structure. If we have such structure, the learning is only easier. There are easier algorithms that can be possible to develop, but that's a good question. So I'll come to the problem formulation in a moment. So for example, in the reward example, instead of designing a reward function, what we can say is probably have a human supervisor, and wherever the robot is probably like, maybe there are 2 robots, and one robot is actually cleaning the room, actually picking up the dust, and another robot is just like covering its visual sensors. So the human can say that I like the first trajectory, the first robot's action much better than the second robot's action. So that could be one way to give feedback, and the reinforcement, this ML agent can try to learn directly from the preference feedback instead of optimizing some hand-coded loss, which can lead to destructive behavior. Similarly, I mean, I can also motivate it from the point of ChatGPT large language model, because even there it has been used to encode a human, like a toxicity and the writing quality of the humans, or the tonality of individual humans. Preference data has been used to actually fine-tune the large language models better. It is there in one of the paper that this OpenAI has published, but I'm not going into the details of it. So the principle, so the main goal of my work has been, and I have been like working on this for since my PhD, is almost to understand that how far we can push this learning through preference feedback. I mean, I want to bypass the reward in some sense, and I want to directly learn from human preferences to build more human-aligned prediction models, which are actually doing what humans intend them to do. We'll study it from a theoretical point of view, and we'll also try to make it more scalable, so that, I mean, when we not only learn from one human, maybe from a distributed number of humans, and we'll see how to also do some distributed optimization, but let's see how much I can cover. So just to summarize some of my work has like several directions. I tried like doing reinforcement learning with preferences, optimization with preferences, also some complex environments that one of this we'll see in this talk. And I have some bunch of work in all of these directions. Particularly in this talk, what we will going to see is how do we build personalized prediction models for human AI alignment problem. So this human AI alignment problem is just to make sure that the AI is actually learning what you want them to do, not just like maximizing some reward. So that's kind of the alignment problem. We'll see an algorithm which is simultaneously computationally efficient as well as regret optimal. And this problem, like kind of a simpler version of this problem has been studied by some of my colleagues at Microsoft Research back in 2015 in a core paper. They were not able to show simultaneously an optimal and computationally efficient algorithm back then, and it has been an open problem since like 7-8 years. When my another colleague Akshay, who introduced me to the problem, and we actually found an algorithm which is simultaneously optimal and computationally efficient. So we'll see this algorithm. In general, I have a little more optimistic objective. So first part of the talk, I would like to cover that. If I have time, I can also try to cover some reinforcement learning with preference feedback. Maybe I'll not cover it for the interest of this talk. I have just some slides. If someone is interested, I'll be happy to explain. In the last part of the talk, I'll also see how to actually extend it to not just a single machine, but if I have multiple, if I'm trying to learn across multiple machines, how do I actually like accumulate the data from multiple machines and learn it in a communication efficient way, also preserving the privacy of the local servers I have. So we'll see if we can cover the third part. Okay. So I'm starting with the problem formulation. So we call it battling bandits more generally because this battling bandits is just a fancy name we came up with for active or online learning with preference feedback. This is kind of a generalization of Dueling Bandit problem, which was invented by Thorsten Joachimson and Isang Wu in Cornell CS department, I think the CS department back in 2009 for some information retrieval task. So I'll start with the problem of, this is the framework of battling bandit, which is much more general, where I'm just learning not from pairwise preferences, but as preference of across a subset of items. But let's start with a simple version of Dueling Bandits here. Okay, so Dueling Bandits, it's a framework, it's a problem, it's a problem framework. The framework basically stands for the problem of active learning from pairwise preferences. This learning could be anything. We'll see this learning could be very generalized. Let's try to understand the frameworks. It's an online sequential process. So at every round, t equal to 1 to t, suppose you have a decision space. Okay, so suppose you have a decision space of k arms here. So this decision space could be just the total number of movies you have in your mind, or the total number of words in the case of large language model, whatever is the size of your decision space. So k just encodes the size of the decision space. Okay, at every point, you as the learner or the learning algorithm, you try to pick two items because I'm trying to learn from preferences. That's the objective. Initially, I have no idea what is your favorite movie. So I know there is only just this K pool of movies available. I want to probably learn your favorite movie through your preference feedback. So this is a very simple problem. How do we do that? So I can initially show you two movies and I can just ask, do you like this movie or that movie? So I can probably do that. At time t equal to 1, I pick two movies or two items or two arms. All of them are synonymous. It's just arms is just a banded nomenclature. So I pick two arms, xt and yt, from this decision space of k arms. And then upon the selection of this, the user, whoever is in my platform, so say I am the YouTube algorithm or I'm the Netflix algorithm, and there is a user who is giving me the preference feedback. So the user is going to give a preference feedback, which could be encoded in the binary 0-1 feedback. So if it is 0, it means that I like the left movie over the right. If it is 1, I say I like the right movie over the left. Something like that. So the user will actually come up with a binary 0-1 feedback from its underlying preference matrix. So suppose if you have chosen xt equal to 2 and yt equal to 4, as we saw before, then the user will simply go to this entry inside his or her head, just toss a Bernoulli random variable. If it is 0, it will output that. If it is 1, it will output that. And it will just give the preference feedback of the two movies, xt and yt you are showing. Of course, you don't know this preference matrix. U means the learning algorithm. You don't know the preference matrix. But often, so how do I measure the regret? And as Arya mentioned, Arya asked that if there is no total ordering kind of thing, it's not very clear what we are trying to converge to. One objective could be just try to be competitive with respect to a fixed item, okay? Maybe there is a best item I star. I don't know what is this I star. This I star could be conversive winner, Borda winner. There are different kind of notions of good arms that voting theory literature or econometrics literature have studied for this kind of choice theory, this choice models. It is not important. Let's say I star is a fixed best arm. So what you can try to optimize is at any point of time t, the algorithm is picking two arms, xt and yt, and you just try to compare how on a relative scale, how much you're off from the best arm, from this fixed arm I star. And also how much you're off from this fixed arm I star in terms of the xt and in terms of the yt, and you just take the average of the two. That can be the total loss of the learning algorithm at time t, and if you sum it over t rounds, that the total loss of the learning algorithm across t rounds. So if you have to actually minimize this regret, note that you sort of need to play xt and yt equal to I star, because if you play both xt and yt equal to I star, then this will be half, because, okay, so one property of this preference matrix is Pij is always equal to Pji. So P14 is equal to 1 minus P41. So 0.56 plus 0.44 is equal to 1. So that will always be satisfying, because the probability by which I like I over j is 1 minus the probability I like j over I. So that sort of an anti-symmetric structure is there. That's why the diagonals is always 0.5. And so when you play xt equal to I star and yt equal to I star, you get half and half, and then there is this minus half, just to make sure that if you play the optimal arm, then you incur zero loss. So you actually incur zero loss if you play the best arm in some sense. So does that regret objective make sense? Does the performance objective make sense? This is one performance objective, but this is no way the only thing. And the objective should very much depend on what the application wants you to do. If you just want to figure out the best movie, maybe this is something you can do. If you want to figure out a ranking, if you can even try to think of that, just coming up with the ranking, or maybe top 5 items. All of this needs to be defined. But so far, does the problem make sense, or someone has any question?
So in each round, you're choosing 2 items,
yes.
xt and yt.
Correct.
Your reward is, your regret is based on the 2 items.
Yes.
You just pick, and you have not made a choice for the arm. Yeah, like, okay, so every round, so you just go on picking 2 items. Correct. And like at some point you,
yeah, that's a different, that you can also study their objective, that you have maybe 100 rounds, and 100 rounds you can play whatever. Now after 100 rounds, you just give me an arm which is the I star with very high probability. Right. So that probably a pack kind of objective, probably approximate correct. You can also study that. But this is just slightly different, kind of slightly different interpretation of the regret, where so in your objective, what's happening is you don't care about what xt and yt you have chosen in the 100 rounds. You're just happy as long as the 100 plus 1th round, you give me an optimal arm. But the regret objective is slightly more conservative. It says that, oh, you are going to be penalized even if you choose very bad arms in the first 100 rounds. So from the very beginning, you have to be conservative and you have to take steps. You don't want to like explore too badly such that you, even in the first 100 rounds, your regret is say order T, and then it's bad. So throughout the trajectory, you want to be optimistic. And the pack objective that you're talking about, it's more like you can do whatever you want in the first few rounds, but at the end, I just want a good arm. Does the difference make sense?
Yeah.
Yes.
So in the preference matrix for the best arm, like all the everything should be greater than 0.5.
That's what is Condorcet winner says. I haven't really defined like, yeah, I star could be the Condorcet winner in case a Condorcet winner beats everything else by 0.5. And it is a very valid notion of I star. I made my I star very general. But
in
yeah.
this case, I star would have been the worst arm.
I mean, generally you should take a max over I star. So here you should put a max over I star. which means that even with respect to the worst possible fixed term, you are optimistic. You are like competitive with respect to the regret measure. But it's not a good objective, actually. We are not going to work on this objective. We are going to criticize this objective anyways. So, and generally, for those who are new to this notion of regret in bandits, generally a good performance for an algorithm, for a bandit algorithm or online learning algorithm is when this average per trial regret goes to 0. This thing happens, which means that eventually you are actually learning the best term. That's why your regret in t time step is something sublinear in t. That's the only way you can have this per trial regret, this average regret go to 0. Which means eventually you're converging to the I star, and you're more and more you're incurring those rounds where you're actually incurring 0 loss. And that's why you have a sublinear regret. So an ideal thing is like square root t kind of regret. That's the ideal thing we can hope for in bandits because the lower bounds has been proved otherwise. And the other objective is to make it computationally efficient. The algorithm should not be like some exponential time, or it should not take like combinatorial computation space or combinatorial memory space. It should be something in polynomial in terms of the size of the decision space and the time. Generally linear. Okay, so let's see if I can. Okay, so this has been the kind of the state of the art. Obviously, there has been many extensions of dueling bandits, but by and large, the problem of generally the dueling bandit objective, there are 3 problems. One is this fixed benchmark I star probably doesn't really make much sense, as already some of you have been pointing out. This could be a very bad arm. This might not be comparative with respect to any of the arm. How does this fixed benchmark make sense? Secondly, why is the preference matrix stationary across the time? I mean, even if the same user coming to the Netflix platform, depending on the mood of the user or season or time of the day, the preferences across the movies are going to change. So the preferences, this internal preference that the user has in their head should not be stationary over T rounds. More importantly, the same users does not show up to your system again and again. There could be similar users who are showing up, and you want to actually predict them good movies, just seeing the preferences of the previous users who could be the friends or something. So you should not be learning from the scratch this preference model from every single user. You should be able to incorporate some sort of personalization, contextualization, so that if you have already learned the good item for friend of Ram, if Ram shows up in your system, then you should not be learning everything from the scratch. So that's the aspect of contextualization, and we'll see how to incorporate this thing. So first thing first, suppose that this is your preference, this is your learning algorithm, YouTube, could be any prediction algorithm. And at T different rounds, say this T user say T equal to 4, this 4 user shows up in your system, and the preference matrix are going to be P1, P2, P3, P4. It should change across time. Essentially, that's the most general way to encode the preferences. Hence, in the regret definition, when I change from P to PT, I star, like comparing the regret with respect to a fixed benchmark, fixed comparator I star makes no sense. So what can we do? So let's try to fix this notion of benchmark here. In standard regret definition, as I said, generally we try to be comparative with respect to max of I star, like a fixed best benchmark. If we put the max inside the summation, maybe that's very strong, actually. So now what it is saying is, you have some preference matrix PT, you play to arm XT and YT. I want to be comparative with respect to the best competitor at that round for that preference matrix PT. It's really strong because this IT star actually can see the PT, it can see your 2 prediction XT and YT, and then choose whatever is the IT star which beats me the most. Okay, so that could be like, that's possibly the strongest notion someone can think of in terms of the regret, because this, if you can do this, if you can minimize this regret, you're really learning the best at every round. But here is a very simple example to show that this is actually not possible to minimize. This regret is actually, I mean, I can always come up with some hard preference matrices, something as simple as like rock, paper, scissors, and make you incur order T regret. How, for example, suppose you have a preference matrix, which is like this rock, paper, scissors. So rock beats paper beats rock, Caesar beats paper, and I think rock beats Caesar. So that's the preference matrix. Now, suppose the learner chooses XT and YT, say it chooses rock and paper. So the IT star, the adversary or the comparator's choice would be rock, because no, comparator's choice would be paper, basically. The numbers wrong. So paper beats rock and paper beats paper by 0 in some sense. So you somehow had a half kind of, when you take an average, you have a half regret at that round. If you play paper and Caesar, then the ID star will be Caesar, you will again be incurring a half regret. Similarly for rock and Caesar, the IT star would be like rock, and you will be incurring again a half regret. So essentially you can always, no matter what you play, I can always make you incur a constant regret every single round. If I'm allowed to see what actions are you taking. So there's no hope of minimizing this regret. So what we have to do is we need to allow the algorithm to randomize. What that means is that the algorithm, whoever is the learning algorithm, that should be able to choose the XT, YT from some distribution. This could be this PT could be some joint distribution over the pair of actions. And IT star can only see PT, can only see your randomization. It should not be able to see exactly the realized value of your actions, XT and YT. Okay, so I'm just slightly relaxing my regret definition, saying that now the learner is allowed to randomize from this PT distribution across the pair of arms, and the best response, like this IT star, this best benchmark, can only see PT, the small PT and this capital PT. It's not able to see what exactly the actions I'm playing. Can we actually minimize this regret, even for this hard instance of rock, paper, Caesar? And turns out, yes, we can, and also in a computationally efficient way. Before that, let's see how do we also incorporate contextualization into the scenario, which I meant by if there are two users who are similar, I should be somehow able to encode the fact that the preferences should also be similar, and I should not be learning from the scratch about the preferences of every single user. So here is the model. Suppose I have 4 users again. Now I know some context. I have some background information about my user. So maybe the demography, some login information, account information. I have some information about this user, their past history. And that is something is what we call as the context. Okay, so C1 is the context of the first user, C2 for the second, and so on. And what I assume is that my preference matrix P1, P2, P3, P4, the individual preference matrix of this corresponding users, is a function of their context, which is a very valid assumption generally. That they have some past history, and their preference at that point of time depends on their past history, depends on their demography, maybe time of the day. Everything could be actually clubbed into this context information. So there is a function f, and this function f maps this context to the preference matrix. Of course, this f is something unknown to the learning algorithm. The learning algorithm has no knowledge what this f is. It just knows that there exists some such function which maps all the context to the preferences. And there could be this function class capital F, which actually can contain all sorts of such mappings, context to preference matrix. I might have the knowledge of this big function class, which contains all the possible mappings from context to preference matrices, but individually, I don't know which is the one for which this is the true mapping for every user's preferences. Okay, so that's the contextualization part. Now let's quickly review the result that I said 2050 work had. They kind of studied this problem for contextual dueling bandits. Their notion of regret was they were trying to be comparative with respect to the policy regret. So what is a policy? A policy pi is just a mapping from a context to the decision space, like set of arms. So that's what we call a policy. So because it's contextual, so every time a new context shows up in your system, the benchmark should very much depend on what the context that showed up in your system. So you have a whole big policy class. This policy class could be like as large as some k to the I think if you have like C, capital C number of contexts and K many number of actions, it could be K to the C or something. It would be very large. And you want to compete with respect to the best policy in the sense that the policy would predict some pi star of CT when you, at time t, when you receive the CT. CT is a knowledge, it's a common knowledge. And you have played XT and YT, so it's the same regret definition that we have seen earlier. It's the same regret definition, except the comparator is just pi star of CT. So it's the best policy. So now the comparator is, I'm trying to be comparative with respect to the best policy. This work by 2015 work, they actually tried optimizing this policy regret, which is not the best response regret though, which is not the regret definition we saw in the last slide. It's actually slightly easier than the earlier, than our notion of regret. But they could not give a simultaneously optimal in both runtime and regret performance. So they gave one algorithm, which is like square root t, which is optimal, but it is runtime inefficient. But they gave another algorithm, which is t to the 2/3, which is actually regret suboptimal, but it was runtime efficient. So they could not achieve the best of both. In this work, we actually worked with a more stronger notion of regret, which we call the best response regret, where the max is inside the summation and all that. Note that why this is stronger than the policy regret, because policy only sees the context. The decision of the policy pi star does not change depending on what XT and YT you are picking. But in IT star can see not only the context, but it can also see the PT, the small PT, the distribution from where you're playing. So it's actually much more stronger than the policy regret. And we have a simultaneously optimal and regret runtime efficient algorithm for this. Is the problem formulation clear, or I should just explain? Because there's a bit of notation here, so I can try to explain. Something is not clear. Okay. Now, this is just a slide to show that the policy regret is weaker than the best response regret that we assume. One important observation before we go into actually the algorithm that we use to optimize this regret, any preference matrix can be seen as a zero-sum game. We already saw an example of rock, paper, scissors. More generally, preference matrix is what I show is basically all the entries are in 0, 1, and the Pij is equal to 1 minus Pji, that kind of structure. That's the only thing we have. Suppose we do a very simple linear transformation. I define another preference matrix P tilde, which is just 2p minus 1. That means all the 0.5 entries are now 2 into 0.5 minus 1. They are now mapped to 0. So all the diagonals are mapped to 0. All the 1 entries remains 1. And if there is any 0 entry, that becomes minus 1. It's just I'm transforming the minus 1 to 1 0 to 1 preferences to minus 1 to 1. Why is this important? Because this essentially means that so when I play two actions, action 1 and action 2, for example, say I play this action, then the gain of the first player is equal to the minus of the gain of the next player. So if if 1 beats 2 with probability, it kind of score 0.06, then 2 beats 1 with minus 0.06. In fact, 2 is getting beaten in some sense. But so gain of 1 is kind of minus of gain, like loss of the other. That's essentially the structure of zero-sum game, and it's a symmetric zero-sum game because P14 and P41 is exactly like anti-symmetric. So because of the nature of the preference matrices. Because it's a zero-sum game, we can try to analyze the Nash equilibrium of this preference game because now it's like a two-player game. What is a Nash equilibrium? Generally, Nash equilibrium means that whenever one player plays from a Nash equilibrium, the other player is never better off playing anything else. In this case, because it's a symmetric game, the Nash equilibrium of both the players, column and the row player, is the same. And the Nash, for example, if I try to define the Nash of the second player, it just says that there are two items, right? P tilde as the preference matrix. So the small p is called a Nash for the second player. If the second player plays from the Nash, so see that Nash is basically distribution over the actions. So if the second action is chosen according to this, should be PT, but this should be PT. Or this PT, this T should not be there. That's it. There should not be any P, but so P is called the Nash equilibrium. If the second player is playing the second action according to this distribution, no matter what the first player is doing, so no matter what action the first player is choosing, it is never able to beat the second action. So that's what the notion of Nash says. In other words, if the first player is playing from the Nash, no matter what the second player is doing, it is never able to beat the first player. Why is this important? Because maybe if we know the original preference matrix, we can simply play the Nash as xt and yt. We can play the xt and yt from the Nash, which means that no matter what it star does, it will never be able to beat me in terms of the regret. And that's the idea. So the only caveat is I don't know this mapping F. I don't know the preference matrix, and hence I cannot play the Nash equilibrium. So what can I do? This idea of zero-sum matrix actually gives us the idea that how to actually develop an optimal algorithm for this problem we have in hand. Generally, there are a few easy approaches which definitely doesn't work, so I'll not go into those. So there is this attempt. Somehow, it's essentially kind of a regression problem because I know the function class from where this mapping F has been chosen. I just don't know which is the true function. Because if I know F, I can just, I see CT, which is the context at time t. I could just compute the preference at time t, F of CT. I just don't know F, and that's the problem. Can I do something like a regression oracle? Because I know the function class. At any time t, I have seen the data earlier so far. I have seen xt, yt, which I have chosen, x tau, y tau, and o tau is basically the outcome. Can I try to use some regression oracle to fit the best function in my function class, and just play the Nash equilibrium of that? So I'm just trying to estimate the best possible choice of F that I have in my function class and play the Nash equilibrium. Well, while this is a good idea, you are not really exploring enough in terms of, because suppose if this F hat at time t that you're computing with this regression oracle minimization, it is a bad choice. You can get stuck in very, very bad local minimizers. Because if you just simply play from the Nash equilibrium, you're really not exploring the other options, the other part of the preference matrix. So you have to have some sort of exploration included. So instead of this, which is basically just playing the Nash equilibrium, I will play something like this less than 0. I'm adding an exploration term. So this term is something we call an exploration term. Why this is exploration? Because if I do something like 1 by PTI, it just says that I'm not allowed to put a 0 weight on any of the decision point I. If I put a 0 in any of the decision point I, then it's going to shoot up to infinity. So I have to put some mass on every single fixed decision I. Of course, I cannot still make it less than 0. So I'll make it something like k by gamma, where gamma is some parameter I can tune. And this is enough, actually. So if I can find a PT at every round, which is almost a Nash, modulo it also has some exploration encoded in it, such that the exploration is not too much. In fact, there is a better trade-off. So it just shows that if there is a arm I, suppose this term is very small, which means that arm I is a really bad arm. It's getting beaten by this PT very badly. Then you can actually put this PT very small, which means that you can maybe not put much mass on that arm I, because that arm I is anyways a bad arm. But suppose if this quantity is actually large, which means that I is actually very competitive with this PT, with this near Nash. In which case you have to put this PTI very large. You have to put a lot of mass on this PTI to make sure it's still bounded by k by gamma. And that's the trade-off this equation is balancing. And
yeah, the thing is no longer a Nash equilibrium, right?
Yeah, it is no longer Nash. It's like a near Nash kind of, yes, Nash with exploration. That's correct. We did not come up with this idea all of a sudden with all sorts of intuition. We solved this entire regret problem as a game between the learner and the adversary, and solved some value of the game, tried to find which is the worst case F and IT star, solve some KKT conditions, and essentially the solution of the KKT condition gave us this condition that any PT, which is going to be comparative for every single choice of F and IT star, any PT should actually kind of satisfy this equation. And then we just interpreted what this equation means. And that's how we came up with actually the solution of the algorithm. So the algorithm is very easy at the end of the day. At every round, it just uses some regression oracle that we already see, just tries to find the best fitting function in the function class f, which best fits the context actions to the reference outcome. And once it has this ft hat, it just tries to solve this equation. It just tries to find a PT which solves this equation. This is from the min-max analysis we have. And just play xt and yt from this PT distribution. PT is nearly Nash. It will eventually approach closer and closer to the Nash equilibrium, but it will also explore with very small probability all the time. And the final regret guarantee of this algorithm looks something like square root kt and the loss of the regression oracle. So when I say loss of the regression oracle, it just means this. So you have this regression oracle ft hat, right? It's always, so what is the loss of this regression oracle in terms of the data you have seen so far across T rounds? So fct of x tau y tau, f theta of x tau y tau is the true prediction, and ft hat c tau x tau y tau is what the predicted output at time t. Sum it over T rounds. That's essentially the total squared loss of the regressor that you're using. If that is small, and you can actually come up with good regression, I mean like regressors which are very, very good, performance is very good. I mean something like logarithmic in the cardinality of the function class when you have a realizable setting and the function class is, say, finite. It's very easy to actually come up with such regressors which has very small regression squared loss across T rounds. And hence we have almost like a square root kt guarantee. Why this is optimal? Because why this is computationally efficient? Because if you look at this equation that we are solving to find the PT, it's actually convex in PT. The first term is linear in PT. The second term is convex in PT. So these are like K convex constraint satisfaction problem. So you can just use some convex programming to come solve for the PT. If there is not a unique choice, you can use any of the PT that you have in hand. We have some follow-up of this work, generalizing to subsets, reducing the strength of the regression oracle, because the earlier regression oracle that we have seen that uses that requires it to be an online regression oracle. It should be able to fit whatever data you are seeing at t time step. Can we actually use something like an offline regression oracle instead, which is reducing the strength of the regression oracle? Can we generalize this to not just pairwise preferences, but maybe subsets, and also like infinite decision spaces? So we have been working on some extensions of this work so far. We have already some results. This is, by the way, a very hard problem. So it like took me almost like 1.5 years of my postdoc, and I felt like my lifespan reduced by 10 years because I used to be so frustrated with this problem. So the extensions are also very hard, but anyways. There are many open problems along this line of learning with preferences, especially from a theoretical point of view. I mean, I try to understand problems from a more foundational point of view, because I think extensions are always possible as long as we understand the basic problem. And even for the basic simplistic setup of pairwise preferences, a lot of open problems are there, which we don't understand foundationally very well. Can I take 10 more minutes or?
Yeah, I mean,
or 7
more minutes maybe.
Okay, sure. Okay, so I'll skip the part where I'm going to talk about this reinforcement learning and preference feedback. This is just to say that when our preferences not just depends on the context, but also depends on the actions that we are taking. For example, if I'm showing you action movies, your preference can actually increase for the action movies. But then if I show you too many action movies, you might get bored and your preference for the action movies can go down. So depending on what XTY you're choosing, your preference can actually get affected by that. So it's like state-based on action, like your preferences depends on the actions the learning algorithm are taking. So that's more or less encoded by the reinforcement learning scenario. And we have some work here. Again, this is even more less explored area of research, and there has been so many open problems. So someone is actually working on it or want to explore this area, let me know. The third problem is actually something I have been looking at recently, and it's very exciting. So I have been thinking that all this learning from preferences problems, say YouTube or training, say personalized healthcare, like coming up with a personalized diet plans or personalized exercise routine, all these things, I'm trying to learn from a human observer, right? So essentially, I'm not even asking you any explicit question. You're using your mobile phone, you're using YouTube on your mobile phone, you're clicking on the movies, and I'm automatically, implicitly getting some feedback from you. So I'm implicitly collecting feedback, but how much feedback can I collect from one single user? It's not really much. I need to, because it's preference feedback, it's really very, I should say, limited kind of feedback. It's very limited feedback. The weak feedback, I need a lot of data to train the model better. And in that case, if I want to make my algorithm scalable, I need to learn across users, which means that if you are using your mobile phone, I'm using my laptop, someone else is using their whatever personalized device, I need to somehow aggregate the data, aggregate the preference data. All of them are all of them are interacting with the systems, but at the same time, I have to do it in a way that I should be communication efficient. I should not be communicating too much across these devices because communication essentially requires money. It is costly. And then I also have to do it in a privacy preserving way because I don't want to know anyone else to know that what movies I'm watching, what movies I'm preferring over the other movies. So there are two challenges when I'm trying to learn across devices. One is try to make it communication efficient. And secondly, how do I preserve the privacy of the individual users or individual local clients? The motivating examples could be, of course, recommender systems, personalized healthcare, chat GPT language models, chatbots, or even like smart text responses that shows up in your email and you maybe choose one of them. So all of them could be an example where this federated setup is very important to learn from. I'll quickly go over the setup, and I might not have the time to just go over the algorithms. If I just need to model this problem, so now suppose I have a decision space, and so far my decision space was this fixed k number of arms, right? If I suppose have infinite decisions, if I just have like many points in my decision space, how do I model the preferences? Because I cannot afford to have a very infinite cross infinite dimensional preference matrix. That's not feasible. So I need to have some sort of structure. So firstly, generally, if the decision space is large or it's like potentially infinite, one way to encode the preference across two items in my decision space could be just assume that there is some inherent scores of these points, and the probability that X is preferred over Y is some sort of link function and the difference of the score function of these two items, which says that if I like some X, if the score of some X is greater than some Y, then the probability that X is preferred over Y is going to be proportional to that. It's just a very standard notion of formulating preferences for infinite decision spaces. And generally, this G could be any function. For simplicity, it could be a linear function or something. Why am I introducing this? Because this is useful when I try to model this problem in a federated setup. I can also assume that my decision space is finite, but I think the infinite decision space or very large decision space makes more sense for more realistic problems. So for every local machine, so suppose I have this capital and many number of clients. For every local client, they have their underlying score function GM. GM could be, for example, linear W transpose, some WM transpose X. X is the item feature and W is the function, essentially. And the preferences are defined like that. Now I said that the users should be similar, because if the users have no similarity, then there is no benefit of collaboration. If the users are completely different, then there is no similarity across the users. I gain nothing by communicating the data. So how do I encode? Okay, first, what do I want to minimize? So I can try to just minimize the similar regret. Now, because I have this underlying score, I can just see what is the total average score of the algorithms across M machines. So I'm summing it over M machines and T rounds. What is the total average score of the algorithm? And what is the best fixed score you can get over all these M machines? You can also make it machine dependent. So you can also make it, like you can also try to be competitive with respect to the individual best item for every single machine. So that could be the notion of performance or the regret in the federated setup. More importantly, more importantly, how do we measure the client similarities? So one way to measure the client similarities could be this W is very similar. Okay, so the total, the norm difference, the L2 difference, or whatever norm difference of every individual W and the average W bar is not too large. The other nice, interesting notion could be that W lies in a low rank subspace. So W is actually some B times V, and B is a low rank matrix. Maybe it's R rank matrix. So then the collaboration should actually give some benefit. We have some results which shows that if suppose the number of message exchanges between the clients and the server is something of less than the order of DMR by 64. So D is the dimension, M is the total number of machines, R is the rank. Then you cannot have a better regret. Like DM square root T is the worst, is a regret you can get even if you do individual optimization in every single machine. No collaboration is needed to get this rate, DM square root T. So this is kind of a lower bound result that shows that if your number of communication bits is less than this omega DMR, you can't do better than the worst case you can do just by running local optimization in every single machine. However, we showed an algorithm where we took number of bits, which is DM, with some additional logarithmic factors. And we show that the regret is, we show some improved regret performance. So this is better, the order-wise, this regret is much better than the DM square root T by some multiplicative factor. So of course, we don't have time to go over this. Also, there is this question of privacy, which of course I don't have time to go over it, but we have some results for defining what is a private algorithm for preference scenarios, which I'll be happy to talk about individually if someone is interested.